Hey everybody, it's Mr. Caudill. Hope you're doing okay. Sincerely, I hope your family's okay. We are almost to the end of this unit. In fact, we're just going to do this one last segment on these things called biogeochemical cycles. They include things like the carbon cycle and the water cycle that you've seen many times all through middle school. So it should be nothing new. And then that's it. We're going to look at our plants that we've adopted outside, and then we're going to review, and then we're going to test. And then we have one more unit to bring us to the end of the year. And that's also on ecology, but it's just a little bit different. It's on populations and stuff like that. Um, I'm going to scan the pages that I'm interested in you looking at in our textbook. I'm going to show you a couple of them right now because I'm going to make my face go away in a couple minutes here. Um, Page 81 has the water cycle on it, the carbon cycle is on page 83, and the nitrogen and phosphorus cycles are on pages 84 and 85. Make sure you can pull those up, follow along with them when you look at this lecture here, whatever you need to do, but that's the level of detail at which I'm going to test. Some of the pictures I show you and some of the movies you're going to see here are a little bit in too much detail. So focus on the textbook pages. That's what I'll have you, that's the level at which I'll require. I'm going to give you 2 days to do this assignment. Then we will, that's Monday and Tuesday, and then we will check out your plans, and then we'll review, and we'll go from there. Okay, hope you're okay. Obviously, I'm not with technology. I just put this picture in here just to show you what would have been. I told you last time that we would have made these big things called eco columns where we take insects and grass and plants and fish and stuff, and we put them all together and we tie together matter recycling and energy flow. I just wish it would have happened. But you can make one. I'll give you the ingredients. You can make one over the summer if you'd like and show me. Well, here we are at our state standards page, and this is one of those state standards that we got, which I didn't really like. It says, explain how ecosystems follow the laws of the conservation of matter and energy. And remember, energy is not conserved. You need a new constant supply of energy all the time from the sun. It's being released out the back end of every ecosystem as heat. It's totally inefficient and wasteful, but matter is conserved, and the matter is similar to water, carbon, nitrogen, phosphorus, these things that we're going to study today. Here are the cycles that you're going to see on pages 80 through 85. Make sure that you read this section. Again, I'm going to give you 2 days to do this, so take your time. And first, let's focus on the carbon cycle. Remember, the carbon cycle you've seen before, where the carbon that exists in carbon dioxide in the atmosphere is pulled into organisms through photosynthesis, turned into glucose, which is C6H12O6, or 6 carbons, 12 hydrogens, 6 oxygens. That's glucose. That's the main fuel source for all living things. That's broken down through cellular respiration and then returned back up to the atmosphere. Here's a movie on this. All living things are composed of molecules that contain carbon. And since carbon is the framework for molecules such as proteins and fats, it is a huge part of existence. Let's take a look at the process that continually recycles carbon. During photosynthesis, energy from the sun is used by plant-like grasses and trees to convert atmospheric carbon dioxide gas into energy-rich carbon molecules. Organisms that feed on plants use these carbon molecules for growth and energy. When plants and animals use the carbon molecules formed during photosynthesis, energy and carbon dioxide are released and returned to the atmosphere. This is done in a process called respiration. Respiration is the reverse process of photosynthesis and releases carbon dioxide back into the atmosphere. Dead plants and animals decompose, returning carbon from the mineralized back to the ground. The long-term process of carbon molecules, which are buried in the earth, can form fossil fuels such as coal and oil. Carbon dioxide is added Sweet. Well, you can't get away from carbon in the atmosphere or the carbon cycle without talking about global warming. You know that too much carbon dioxide in our atmosphere causes a blanket of gas high above the Earth, which traps reflected solar radiation, meaning just the sun's rays that hit our planet and then get bounced back towards the space. And usually they just go out into the vacuum, cold vacuum of space, and they're gone. But what happens is that we have this layer of carbon dioxide and other gases which trap that heat. Now, it's very important that we do have that layer. If we didn't have the layer, scientists believe our planet would be about a minus 200 and something degrees Fahrenheit, like super, super cold. So we have to have that layer. The problem is that the layer is getting too thick and we're trapping in too much heat as far as what we've been used to. Um, so maybe we can start to do things to lower our greenhouse emissions or reduce that layer somehow. You know, one good thing about that is that you probably never have to worry about this again. And you'll definitely have a washed bike, that's for sure. So, yay, the carbon cycle. So, you can follow along. Like I said, if you want to pause this, you can take a look at page 83. I'm just looking at the textbook now. That's where it is. The next cycle we have to go over is the water cycle. And I know you've been doing this for years ad nauseum. It's on page 81. Here it is. Just remember evaporation, condensation, precipitation. Some people say that the water that's in your glass that you're drinking today was once in a dinosaur's bladder and left the dinosaur's urine. You know what I mean? It just go. The point is that water molecules, they just go and they go and they go and they get recycled. I once read that in North America, um, uh, the water that's in your toilet has been flushed down 8 other toilets in the water's lifetime. So anyway, water is recycled, and water that you're using today will eventually be used again, maybe 10, maybe 50 years from now by someone else. Take a look at the water cycle on page 81, please. And then you have to understand that nitrogen is super important for us because we use nitrogen for a variety of things, specifically the amine groups in amino acids. There's two sides to an amino acid, and one side is an amine group, and it has a nitrogen atom in it. There's tons of nitrogen around, specifically in the atmosphere. In fact, 80, what is it? 78% of all gas in the atmosphere is made up of nitrogen gas, N2. The problem is that it has a triple bond, and we can't break this triple bond in our body. So we inhale nitrogen, gets into our lungs, and then we exhale it. We can't get it. The only way we can get it is through food. And we either get it from eating meat or eating plants, excuse me, and then the meat that we eat have eaten plants. And the way plants get nitrogen is they use these things called nitrogen fixing bacteria on their roots. And those are the only things that we know that are able to break atmospheric triple bonded nitrogen into its two component parts, into two individual nitrogen atoms. So I would have shown you this on the board, but you'll read about it in the book. Well, this is a pretty simplistic diagram. I didn't have the diagram that exists on page 84 in this PowerPoint. Make sure you look at that, please. Here's our little movie on the nitrogen cycle. Like say you're on a lifeboat in the ocean and you're super thirsty, and there's 300 million cubic miles of water sitting right in front of you, but you can't drink any of it. So you're having to sit next to Meg and count every day you walk across the water is really dramatically out of your league. Everyone is trying to find themselves in this situation pretty much constantly. Except that the thing that's everywhere that they can't have is a water physically closeness. It's nutrients, specifically nitrogen and phosphorus. Suppose there are tons of elements that cycle around the earth, hanging out in one place or flow for a while before moving on to the next. And as you know, living things need a bunch of stuff. Animals, for instance, need oxygen, carbon, and hydrogen. These elements basically cover the water cycle and the carbon cycle that we talked about last time, but we're also about 3% nitrogen and 1% phosphorus. So it's not really quite on top super significant, but even though we've just got teensy bits and stuff in our bodies, we need nitrogen to make like amino acids, which make proteins, which make our whole bodies up. And DNA and RNA too. DNA and RNA also require phosphorus, not to mention that phosphorus is the P in ATP and the phospholipid bilayer. So we might not need to tell you this
but it is important. And it's happening everywhere. The air we breathe is mostly nitrogen, and the water and rocks all around us are jam-packed with phosphorus. And it's like they're running into biological emitter. And as per usual, the organisms that solve this problem are the plants. Anything else that needs these nutrients are just going to have to eat some plants or need something to eat some plants. So how do plants solve this problem? And why is it a problem in the first place? Well, give me a few minutes. I'll explain. So let's talk about the nitrogen cycle first, since nitrogen really is actually all around us. I can feel it right now. There it is in the air. So why does it so happen to get the stuff that's constantly surrounding us in the air to actually bodies to be useful for us? Because even though nitrogen gas makes up about 78% of the atmosphere, you notice here that nitrogen gas is made up of two nitrogen atoms stuck together with a triple bond. That's right, a little bit of silicon in the bond, but three. So as you can imagine, those two nitrogen atoms are totally apart. Now, has to be split in order for a plant to get pieces. In fact, plants can assimilate a bunch of different forms of nitrogen. Nitrates to our muscles, like ammonium, which is what you get when it's ammonium with water. And all that bad nitrogen gas in the atmosphere is beyond their powers of assimilation. So plants need help taking advantage of this portion of nitrogen that we're asking them to do, which is why they need to have that nitrogen fixed so that they can use it. Even though plants aren't bad enough to render those two nitrogen atoms apart, certain nitrogen fixing bacteria. These bacteria have similar water proximal relationship with boundaries of some plants, most of which are legumes. That's a pretty big family of plants. Soybeans, clover, peanuts, colza, algae. So these bacteria just sit around and burn atmospheric nitrogen into ammonia, which then becomes ammonia when it's with your water, which can be used by plants. Even there's with a special enzyme called nitrogenase, which is the only biological enzyme that can break that crazy triple bond. Ammonia can also be made by composers, fungi, fungus, other kinds of bacteria that munch on their proteins and DNA to die. But they're not picky. They like poop and urine too. Then once this has happened, other bacteria, known as nitrifying bacteria, can take this ammonia and convert it into nitrates. Three oxygen atoms attached to a single nitrogen atom. And nitrites, two oxygens attached to a nitrogen. And those are even easier than the name for plants to assimilate. So the take home here is if it wasn't for these bacteria, then that's the biological ability of nitrogen hanging around, and as a result, there are really not few living things on the planet. So as usual, thanks bacteria, we owe you well, but I should mention that it's not just bacteria who can be able to nitrogen ions. Lightning, of all things, has an ability to break the bonds between nitrogens.
Okay, that's pretty cool. I will say nitrogen is also important in DNA, nu- sorry, deoxyribonucleic acid. And so these are nucleic acids, and these A's and T's and C's and G's, they have nitrogen as their base component, and these bases that then kind of reach across the middle of DNA and form hydrogen bonds with each other. Let's move on finally to the phosphorus cycle. I'm going to tell you phosphorus is super important. You're going to see phosphate groups and ATP. You learned about that when we break down glucose and cellular respiration to make potential energy. Also, phosphorus is found in the phosphate groups in the backbones of DNA. Um, uh, how we have alternating sugar phosphate groups. So we definitely need phosphorus. And I'm going to tell you where most phosphorus resides. It resides in rocks. It's usually not available to us unless that rock has been eroded by some sort of rain or wind event, and it gets into bodies of water usually, and then it eventually those bodies of water go away, like old seas and oceans, and then there's phosphorus there in the ground, and then plants grow and they assimilate that phosphorus. I do have a movie on phosphorus cycles as well, but first I want to show you uh, the phosphorus cycle, which exists. I'm looking at the book on page 85. Make sure you take a look at that. And here's my little cartoon on phosphorus. This is Phosphorus Family. Let's go on a trip to the beach. Look, it's the Grand Canyon. Wait, Phil, stay in the car. No, Mom, you can't keep me from where I belong, with the rocks. Philip Phosphorus, get your sediments back in this car. And you can see here that phosphorus can remain locked in rocks for a long time. So when you go through the Glenwood Canyon next time, make sure you look at the rocks and say to yourself, or better yet, annoy the people in the car whom you're with and say, wow, there's a lot of phosphorus locked up in those stones. Okay, we are done. And I'll give you your assignment. Just know that phosphorus is super important. It's mainly stuck in rocks or in these biological cycles where things will bring it in or assimilate it into their bodies, either bacteria or plants. Those things are then eaten, and then it's put into bodies of organisms like us, and then eventually organisms die. They decompose. The phosphorus gets put back into the soil, and new plants come and grab it and use it again. So um, phosphorus is just used in a constant cycle. Here's your assignment. I just want you to make sure to read 6 pages in your book and answer 4 questions. You can do that in a Google Doc and send it to me when you're done. I'll give you another day to do this assignment. Thanks for listening. I hope you are safe and healthy. And we're done with this unit. We'll just come in for a nice soft landing here, and then we'll take a test probably next week. Okay, thanks.